And we are live. What is up, everyone?
Hey.
For another night of SAT crams. We're going to talk about everything to do with advanced math, additional topics in math, all that fun stuff. But before we jump right in, just a few little introductions. My name's Dylan. I'll be taking you through the first half of tonight's content. I'm a third-year history and economics major at Northeastern up in Boston, a math minor. Super excited to be talking to y'all about all things math.
Hey guys, I'm Tammy. I am a freshman majoring in computer science and also minoring in math. So I didn't know that about you, Dylan. But yeah, I'm super excited to be here too.
Awesome. So let me pull down the slides here and we can get started. Let me see. There we go. Okay, cool. Let's jump right in. All right, so like we talked about, we're going to be going kind of over the second half of the math section tonight. All things, advanced math, algebra, geometry, trigonometry, some statistics and probability. It's going to be a fun night. So before we jump into anything, make sure that if you're not already, follow Fiveable on social media, on TikTok, Instagram, YouTube, LinkedIn, any of those social media platforms. If you want to be in the loop about what's happening, about what streams are happening when, make sure you're in the loop and know when streams are happening. All right, so if you're here, you've already unlocked cram mode, but just so you know what you've unlocked with that, you've got access to practice questions, cram finales, study guides, study plans, and you're the first ones to know about new features. And so as we release new things, we'll make sure that you guys know what's going on and have all of the firsthand information as we release new features to help you on your SAT and ACT. So just before we kind of jump right in, just some kind of community agreements, just to make sure that we're all kind of respectful and supportive of each other, right? We're all trying to do our best on this exam. Feel free to use the chat on the right side of the screen as your own space to ask questions, to talk to each other, chat. I'll be monitoring it, and we have a few other people monitoring it through the stream, but feel free to use that as your place to kind of ask questions. If you have kind of a big picture question, feel free to drop that in our Q&A section as well. We'll be going through those kind of throughout and definitely at the end if we have time. But if you have any questions about what we're talking about in the moment, feel free to use that chat. Use the chat, to your advantage. It's there for you guys. All right, so here's kind of a big picture look at what we're going to be talking about tonight, right? We're going to jump in with some trig, some radian stuff, move into some circles, some geometry, some circle theorems, talk about all of the kind of algebra things, the polynomials, the exponentials, the rationals, and really jump into kind of how those work together, different types of problems you could be asked with it, and how to handle all of those types of functions on the SAT. Then we're going to be talking about, I think at that point, Tammy will jump in, and she'll talk you guys through some geometry, some complex numbers, and then we'll do a whole bunch of practice to round off the night, along with some Q&A if we have time. Again, if you guys have any questions about specific material, feel free to drop it in the chat. We're happy to talk about what you guys need to study. So let's just talk about quickly, if you've been studying for the SAT this Saturday, you've probably already come across these things. Let's just talk about kind of what the SAT math looks like broadly. So first and foremost, right, the math section, you have two major sections in the SAT math. You have the no calculator and the calculator section. And they're kind of relatively similar in question style, but just different in length. So on the no calculator section, you'll have 25 minutes to answer 20 questions. It's a very snappy, quick section, which is around 75 seconds per question. You have 15 multiple choice and 5 grid-ins. So grid-ins are kind of where you get a little grid to scantron in a real number, as opposed to an A, B, C, or D. On the calculator section, it's a bit longer. It's around a 55-minute section for 38 questions. You get a little bit longer per question, primarily because they need to give you a little bit of time to type on your calculator. And it's 30 multiple choice questions and 8 grid-ins. So again, it's kind of an interesting number of questions, but you get a little bit more time per question. We will be talking about kind of the pros and cons of the calculator section or no calculator section, and we'll see a number of examples of each as we go through. This is the formula sheet for the SAT, right? So you've kind of got everything that you aren't expected to memorize on here. So that's kind of most if not all of your geometry formulas, your special right triangles, your volumes, some information about the degrees and radians of a circle, the angles of a triangle. And so I have a really kind of love-hate relationship with formula sheets because at the end of the day, these are things that I feel like you should know primarily for speed reasons, right? Like if you're flipping back and forth in your exam, it's wasting time. It's there for your reference. I really love that, right? They don't expect you to have things fully memorized. But I'd argue that you should know some of these off the cuff, right? You should, for example, I'm sure we've all taken the area of a rectangle before, or we've all, found the area of a triangle before, right? These are things that you should kind of go into the exam being comfortable with. And even if you need to quickly flip back to get the quick nitty-gritty specifics, you should be comfortable with like knowing which of these formulas to use when, because that's not what the formula sheet tells you, right? So I feel like a lot of people use this to mean, okay, I don't have to study volume of a sphere. But in reality, there are many problems they might give you where you have to apply that knowledge of how to find the volume of a sphere without actually just being like, if I have a sphere that the radius is x, what's the volume, right? There might be other steps involved that then like coincide with using this formula. So memorizing is nice, but understanding is better. All right, so speaking of geometry and formulas, let's jump right into trig, right? Everyone's favorite part of the SAT. One of my favorites, at least. Everything to do with sines, cosines, tangents, how we measure angles, triangles. Trigonometry is really fun, and actually is usually one of the easier parts of the exam because there's only so much they can teach you in trig without going crazy. And so a lot of the time, the trig questions on the SAT are actually primarily kind of do you know it or do you don't questions, or do you not questions. So let's jump right in. So kind of the big 3 or 6 things you need to know for trig are the trigonometric functions, right? So those are all based off of a right triangle, right? So we have this right triangle here, triangle ABC, and we've labeled one of its angles as theta. Theta is just a Greek letter meaning kind of measuring the angle. And we define 6, but mainly 3 functions off of this theta. We define the sine, the cosine, and the tangent. And these are specific values that relate this angle to the ratio of sides of a triangle. So, for example, the sine of an angle is the length of the opposite over the hypotenuse of the right triangle formed by that angle. So, for example, in this example, the sine of theta would be A over C. The cosine is the adjacent side, so not the opposite, but the adjacent over the hypotenuse. So that's B over C in this example. And the tangent of theta is going to be the ratio of the opposite to the adjacent, so A over B. What's interesting is that this value will always be the same for the same value of theta. So don't freak out over like, if you know that the sine of some angle is like 0.74 and you get a fraction that is 0.74 but isn't like exactly the fraction you remember. The sine of an angle is a constant. So you'll always get the same answer of like the sine of 30 degrees is the sine of 30 degrees, whether this opposite side is 50 or 5. So something to kind of note. And those are the 3 big ones, right? Those are the ones that really you're going to be asked about in the SAT, asked to find, asked to talk about. But there are 3 what we call reciprocal formulas. And those are 3 functions we define as the reciprocal of sine, cosine, and tangent, respectively. So we have 3 functions. We have cosecant, secant, and cotangent, which are respectively defined as the inverse of sine, cosine, and tangent, or just if you flip these 3 fractions here. Something that's kind of annoying about this is that cosecant doesn't map to cosine, it maps to sine. But that's just kind of something you want to remember. Other than that, they're kind of the exact same idea, right? Taking an angle and relating it to the ratio of the sides of a right triangle. That's all a trigonometric function does. It's just a relationship between angles and sides. And what makes them so useful is that if you know an angle and a side, you're able to find that other side because you know what the relationship is between that angle and the sides. And we'll see some examples of kind of how we actually apply trig later. There are also a few kind of interesting kind of key functions that are useful. They might not come up directly on the SAT or might not be completely necessary, but they're always helpful. There are many questions where using this might be helpful, where if it's easier to find the sine of an angle rather than a cosine or something like that. So for example, the sine and cosine functions are actually complementary functions. And what that means is that the sine of theta is equal to the cosine of the complementary angle to theta, right? So the sine of theta is equal to the cosine of 90 minus theta. So if you think about this, the sine of 30 is equal to the cosine of 60. And the same thing applies kind of if you flip them. The cosine of 60 is the sine of 30. So that's really important because if you are faced with a problem where you can very easily find a sine, you can very easily find the cosine of its corresponding angle because its complementary angle because they're equal. Similarly, if two angles have the same sine, or excuse me, if two angles have a relationship where the sine of one is equal to the cosine of the other, then we know for a fact that they're complementary angles, right? This is the definition of sine and cosine being related to right triangles, right? If you kind of think about this, if we go back to our previous slide, if the sine of this angle, A over B, is equal to the cosine of this angle, A over C, right? These are the exact same, right? These two are complementary angles by the definition of a right triangle. And so A over C, the sine, is equal to A over C, the cosine. So it's actually kind of a trivial relationship here, right? That if two angles have the same sine and cosine, then they have to be complementary because what it tells us is that they're corresponding angles in a right triangle. So just some kind of logic there to help you understand it as opposed to memorize. There are a few kind of trig identities as well, kind of relationships between these functions that are important to know. You won't need to know how to prove these, right? There are no proof questions on the SAT, but they're very useful just in kind of understanding them. So the big one is called the Pythagorean identity, right? And that tells us that sine squared plus cosine squared equals 1. You can kind of think this out if you are familiar with a unit circle. This should feel kind of trivial by applying the Pythagorean theorem to any angle on a unit circle. But again, we're not here to prove. And then these two Pythagorean identities are formed by dividing through by either sine or cosine and then solving. By inverting the whole thing. So doing 1 over sine plus 1 over cosine, 1 over 1, and you get secant squared and tangent squared. Or excuse me, I'm so sorry. By dividing through by sine or by cosine. Secant squared or these cotangent squared or the tangent squareds. So that's where those two come from. This is the important one. These other two kind of are natural consequences. They follow directly from this Pythagorean identity. So something to note, you'll probably aren't going to see this on your SAT, but it can be helpful just in thinking about certain problems. If you know the sine of something and then you know the cosine squared of the other thing, which means, or the cosine squared of the same angle. And so that's kind of a useful identity. If you know the sine of something, then you know the cosine of that thing because the sine squared plus cosine squared equals 1. Okay, so let's look at an example here. This is some coordinate geometry and some trig kind of combined. So we see right triangle ABC is shown in the XY plane above. What is the value of the cosine of C? All right, so we have 4 answer choices here. I'm going to give you guys 1 minute to answer this question, a little less time than you get on the SAT. So if you're not able to get fully through it, don't worry, just for the sake of time. And then we will go over the answer. So 1 minute starting now. All right, that is time. All right, so let's start talking about kind of what strategies we could use on this question, what we already know, and what we need to figure out in order to find the cosine of C. So first and foremost, some notation. When they say the cosine of C, they mean the cosine of this angle right here attached to point C. So this angle here, oops, there's the answer for you. So we know the cosine of C is going to be this side, BC, over AC, right? Just by the definition of cosine. We have these 2 points, so we can figure out this point here to be, well, it shares a y value of -3 with C, so the y value is -3, and the x value is -3, so that point has to be the point -3, 3, -3, -3. Excuse me. And from here, we can figure out the lengths of A, B, and C. Actually, we can figure out the whole right triangle by using the Pythagorean theorem. We figure out A, B, and BC by just subtracting numbers, because they're horizontal and vertical lines. So their lengths are kind of trivial. And then the hypotenuse we find via the Pythagorean theorem to find to be 17. And then we're able to quickly take the ratio of BC, which is going to be 12 plus 3, 15 over 17, as we figured out. And that gives us our answer of D, 15 over 17. So if you guys have any questions about that, about how that works, about what we've done here, how we figured something out, feel free to drop in the chat. We can always come back to this. So yeah, so if you have any questions, feel free to ask. Otherwise, let's move on to some more material. All right, so radians, right? I'm going to kind of move quickly through this because it is on your SAT, but it's not going to be a huge part, right? But it's worth knowing. So radians are a measure of angles, just like how we use degrees. Radians is just another way of measuring kind of the size of an angle. The way we define radians is different than the way we define a degree, in that a degree is defined as 1/360th of a circle, right? And the reasons we choose 360 are numerous, but that is actually kind of an arbitrary choice. But anyway, we choose 360, right? 1/360th of a circle, 360 rotations. A radian is more, actually, I think, a more natural way of looking at a circle, and that's by looking at how many radii can you fit around this circle, right? So if we take this radius here and kind of curve it around that circle, the angle that forms that arc, the angle that forms that arc is defined as 1 radian by definition, right? It is the angle that creates an arc with length r. Something to note is, think for a second, how many radiuses can we fit around a circle? Well, we know the circumference of a circle is 2 pi r, so we can fit 2 pi radians in a circle. So what we know is that 2 pi radians is equal to 360 degrees. That is a key relationship right there, right? 2 pi radians is the same as 360 degrees. I'll say it again. 2 pi radians is equal to 360 degrees. So what we can do is, with this, now that we have a relationship between radians and degrees, we can actually just convert between the two by either multiplying radians by 180 over pi or multiplying degrees by pi over 180. And the reason we have 180 over pi or pi over 180 is that is 360 divided by 2 pi, right? In this case, we cancel out the 2's. So 180 is half of 360. Similarly, you can think of it as, well, if 2 pi radians is 360 degrees, then pi radians must be half a circle, right? Roughly, you can come and see it, right? It fit like a little over 3 radians in half of a circle, and a little over 6.28 in a full circle. And so that's where radians come from, and where converting between the two comes from. Right, so some conversions, right? We've talked about this. On a coordinate plane, an angle is defined by its relationship to 2 rays, right? So if you have 2 rays, you define an angle. So in this case, these 2 rays are these 2 radii. In the other case is the relationship of this angle, or of this ray right here, right? These 3 rays with the initial side, which is the ray formed by the x-axis. In this case, this angle's measure is 135 degrees. We can also measure angles negatively, right? If we measure angles positively by going around, we measure them negatively by going clockwise. And that also brings up an interesting point of, there are actually kind of coterminal angles, which are angles that are the same in a 360 degree kind of way, right? If we go forward 60 or backwards 300, we end up at the same place. And so 60 and negative 300 are coterminal, right? They have the same terminal side. So just some kind of vocabulary that I might be using throughout tonight. Excuse me. All right, so this is some Radians practice. I'm just going to go through this question. Let's see, do we have time? No, actually, I think we're good on time. So I'm going to give you guys 1 minute to go through this question. It has to do with your knowledge of radians and degrees, and specifically also some knowledge about how to convert between the two and how to interpret this geometrically. So 1 minute on the clock. Again, if you guys have any questions, feel free to drop it in the chat or in the Q&A section, and I'm happy to answer them. All right, that is time. All right, so let's start thinking about kind of how we want to approach this question. So we're told we have some circle here, circle D, right, marked by the center point D, and an equilateral triangle ABC right here. That's important. It's equilateral. Something to keep in our head. And we want to ask, what is the measure in radians of angle ADB? Right there. So there are a few kind of ways to think through this question. The first is going to be, actually, I think the simplest is looking at the fact that an equilateral triangle like this is going to take up a third of the circle each time, right? If this is equilateral, then these three angles are equivalent, meaning this is a third of the circle, this is a third of the circle, and this is a third of the circle. Well, what do we know about how radians relate to a circle? Well, we know that there are 2 pi radians in one circle. So how many radians are there in a third of a circle? 2 pi over 3, right? That's exactly kind of the same measure it takes here, but first it finds that these 3 parts are 120 degrees, and then takes those 120 degrees and converts it to radians. So that's how you kind of use the formula pi over 180, but you can also just logic this out, right? Again, understand that radians, all radians do, what a radian means intuitively is it is a percentage of the circle, right? 1 radian is 1 over 2 pi percent of a circle, or excuse me, not 1 over 2 pi. I don't want to think about it in terms of percentage, but it's 1 radian, right? If pi radians is half a circle, right? So 1/3 of a circle is 2 pi over 3 radians, because 2 pi is the whole. You could always, again, use degrees and then convert to radians. But if you just think of a certain ratio of percentage of radians as a part of the circle, right? 3 pi over 4, well, that's like saying that, you know, or okay, let's look at 4 pi over 5, right? That's like saying that this takes up like a well over, excuse me, these are all saying that it's making up a bigger percentage of the circle than 2 pi over 3, right? Because this is saying 3 half circles over 4. This is saying 2 full circles out of 5, and this is saying 2.5 full circles out of 6. This is saying this is saying 1 full circle split in 3. So that's exactly what's happening here, right? 1 full circle being split into 3 parts. Those parts are each of size 2 pi over 3 radians. But again, you could always, I know this is a very kind of convoluted discussion of radians, but what you could always do is just convert this to degrees and then convert to radians. Okay, so let's start talking about circles now that we've kind of gotten our whole circle jam in. There's a ton we can talk about with circles. So much. I love circles. I love circle equations. I love math with circles. So let's jump in. So a little bit of vocabulary before we get started, just so we're all on the same page about what words I'll be using. So we have this diagram here with some different parts of the circle, and I'll talk about some notable ones as we go through. So this right here, SQ, is a diameter of the circle. OQ is a radius. The radius is half the diameter. And a radius stems from the center of the circle to the edge of the circle, right, to the border of the circle. And the distance from the center to the border is the definition of the radius. A chord is a segment of a line segment whose endpoints are on the circle. So for example, this chord here, the diameter is a chord. But for example, this right here, OP, is not a chord because its two endpoints are not both on the circle. We then have tangent lines, right? A tangent line is a line that just touches the circle at one point, only one point, right? So it almost just kind of comes in, blanks it, and then leaves. And then we have a secant line, which is the opposite of a tangent line. A secant line touches the circle twice. It can also be thought of as the line containing a chord because it passes through 2 points on the circle. So those are all just some words I'll be using tonight. Want to make sure we were all familiar. We'll be talking about kind of some properties of specifically diameters and radii and angles related to them. Chords, secants, and tangents. Worth knowing, worth understanding, typically not super important. There's one fact of a tangent that's kind of important, and that I don't think is in the slide deck, so I'll just say right now. The line from a tangent, the point of tangency to the center, this line segment right here, is perpendicular to the tangent. So just something worth remembering. So any radius that intersects the tangent line like this is perpendicular. It's kind of easy to see that in your head. So some angles, right? We've talked about all the different line segments we have in a circle. Well, what about all the angles that we have in a circle? So first we have central angles, right? And that is an angle whose vertex is the center of the circle, right here. That makes sense, right? Central angle, part of the center. So that is angle POQ right here, right? Is a central angle. An arc is a part of a circle defined by a central angle. So for example, PQ is an arc, SP is an arc, SQ is an arc, SR is an arc, SQ is an arc. No, you don't see the central angle for SR. Excuse me. But the angle is clearly, you look, S to O to the center and O to R, it's that angle right there, right? We think of it as kind of taking a piece of the circle. The measure of an arc is defined by this angle, right? So the measure of arc PQ is whatever this angle is here, right? It looks to be like 45 degrees or so, maybe a little more, 50 degrees, right? The measure of a semicircle is, as you can see, 180 degrees, right? The angle defining SQ is this full 180 degrees, half the circle. There are also, for every arc you create a minor arc or a major arc, right? You have arc PQ, right? PQ is a minor arc, and you have a major arc. You have a major arc PSQ right there. Or I guess I think down here they define it as look real quick. This is QPS, oops. PQS right here. Yes, okay, so that is a major arc right here, right? PQS and SOP is its minor arc. So just some vocabulary to get you guys through. All right. So let's start talking about arc length, right? We've defined these arcs based off the measure of their angle. Now, how do we figure out how long they are, right? What is the length of the arc? Well, the length of an arc is just a part of a circle, right? We know this because we just can see it right there. You can see that that is a part of the circle, right? That's what an arc is. So the measure of an arc is the degrees that we talked about, right? So for example, this arc right here is an arc with 82 degrees, right? That's the measure of the arc. So the question is, how do we find the arc length, right? This length of this segment AB. Well, we can use this by kind of thinking about the proportionality of arc measure and arc length. Specifically, if we know the arc measure, we know what percent of the circle it takes up. And if we know the circumference, we know what the total is. So we know that we have arc measure over 360. So for example, 45 over 360, 32 over 360, 82 over 360 is the part of the circle it takes up, right? Part of the whole. And then we have the arc length over the circumference, which will be the exact same fraction, right? We know this because we're taking up a certain chunk of the circle. So arc measure over 360, what percent of the angles are we taking up, is exactly the same as what percentage of the total circle are we taking up. From here, we can just multiply through by 360. Yes, okay. We can multiply through, or excuse me, we can multiply through by circumference. That's exactly what's happening. Multiply through by circumference to get that the arc length is equal to the central angle over 360 times circumference. And this should actually make some pretty decent intuitive sense, right? Well, if we have this arc length right here, it is equal to some fraction of the whole, right? 82 over 360 in this case, times the circumference, times the whole. And that will get you the length. Basically saying, what percentage of the circumference is this arc taking up? And then from there, we can find the actual length. And the same goes for radians, right? Again, radians is uniquely tied to the circle, right? And specifically to the length of radius. So for example, in this case, if we know the radius, right, we can define the radian measure as theta, like we always have. Well, we know that this s is going to be a certain number of radiuses when theta is defined in radians. And so s is going to be theta radiuses, right? 1 radian, the length of it is 1 radius. We define radians in terms of an arc length. And that's why this is such a useful formula and such a kind of easy formula, right? You can almost say it out loud. The arc length is asking how many radiuses do I have? Do I have 2 pi radiuses? Well, wait a minute. 2 pi radiuses, that should sound familiar, is circumference. So if I say I have 2 pi over 3 radiuses, that means 1/3 of the circle, right? That's why radians are so useful. It's because they relate things like arc length and circumference and angles all together in one number. That's why a lot of the times you'll see mathematicians actually not using degrees. You'll see them using radians, even though the high schoolers a lot of the time, a lot of the time we'll go, well, why do we need to learn this? It's because they're actually really useful. They give you a relationship that 360 degrees doesn't, because the measure of a radian is tied distinctly to the circle. And that's what makes them so useful. So here's some practice. So I'll give you guys a minute to do this. And it tells us in the figure above, the radius of the circle is 8. So it's marked right there for you. And the measure of angle AOB is 120. What is the length of AB? So 1 minute on the clock. Actually, this isn't really actually an arc question, but it's still useful. All right, that is time. Let's start talking through how we would approach this question right here. Seems like my screen's a little less laggy, so let's turn this back on. There we go. So we're told that the radius here is 8, and this is 120 degrees, and we want this length right here, right? So you could be asked for the length of AB, right? And the way you know that it's asking for actually the length of the line segment is because of this notation here, right? So the notation otherwise would have looked like, let me see if this will work. I've never used this before. Ooh, this is awesome. It would have looked like AB and it would have been like an arc, as opposed to AB, right? Now it looks like it's got a little top hat on, which I think is cute. All right, so how do we approach this, right? We know this is 180, so it's not a right triangle, so we can't use the Pythagorean theorem, but I would love to, right? A lot of strategies in math comes down to, I can't do something, but I would love to. How do I force the problem into doing what I want, right? It's almost one of those, like, the problem is more scared of you than you are of it. So in this case, what can we do to this circle, or to this triangle, excuse me, to turn it into a right triangle? Well, my first thought is to just chop it in half. Create two right triangles. So we've done this, and we know that this is a perpendicular bisector. And the reason we know this is because AOB is isosceles, right? We know that because these are both radii. And so an altitude dropped from the top of an isosceles triangle will always bisect the other side. And this can kind of, again, you can see this in your head. So I'm not going to kind of exhaust a proof out because you don't need to have a proof. If you'd like a proof, I'm happy to kind of try. But so yeah, so we've kind of created these two right triangles, and now we've got the problem doing what we want, right? It's fallen into our trap. So now is the rest of the problem. All right, so we have these two angles, AOC and BOC, which are each 60 degrees, right? We've bisected the angle, right? So this is 60. What do we know about a right triangle that has 60 as one side, or one angle, 30 as the other? We've got a 30, 60, 90 triangle right there. So we know that if this side is 8, then by the definition of a 30, 60, 90 triangle, OC is 4, and CB is 4 radical 3. Right? That's what this work down here just says. And you can figure that out by, if I go back all the way, it's right there on your formula sheet, right? The side across from the 30 degrees is x. That means the hypotenuse is 2x, and the other side is x rad 3. Right, so that's how we figured that out. It's on your formula sheet. And from there, if we know that this is 4 rad 3, we know that this is 8 rad 3, which is B. Also, when I say 8 rad 3, I mean 8 square root 3. And also, yeah, let me grab you the slides. Okay, I can't share the slides because I'm not signed in. If one of the other hosts could share that, that would be great. It'll be probably showing up underneath the screen in a second. Sorry, we usually share them. All right, so let's talk about circumference and area. All right, so we have kind of talked about this, but circumference and area is given to you. Circumference is 2 pi r. We now have some more knowledge about why that is, right? It's 2 pi r because it's 2 pi radiuses, 2 pi radians, right? And the area of a circle, pi r squared, bit harder to prove. I'm not going to, but there's reasons why, and you can prove that via calculus, so I won't. But these are the two biggest equations when it comes to circles. Okay, so the circumference, like we said, is the perimeter of a circle, right? It's just this right here. And the area is the total space inside, right? I'm going to assume that we've all kind of seen area and circumference at least once before in our education. So I'm not going to dwell on it too hard. If you'd like me to, happy to. But I'm going to assume that we've all at least seen this before and move on to some more content. Okay, so we have another practice question here. So this question is asking, the circle above has an area 36 pi and is divided into 8 congruent regions. And it's asking us, note what it's asking for. It is asking for the perimeter of one of these regions, not asking for the circumference of the circle, not asking for the radius of the circle. It is asking for what is the perimeter of this bit. So you need to figure out what is the radius and what is this arc, right? And then we can find it. So I'll put 1 minute on the clock and let y'all play with this. So 1 minute starting now. All right, that is time. This is a fun problem, a very fun problem. And I just saw in the chat, the slides are now up. If you look underneath the stream, you will be able to get a copy of the slides. All right, so we're told this circle is an area of 36 pi. And again, what I would love to have, again, this is a really interesting problem solving technique, a really good one, is you go, I know what I have, what do I want, right? What do I wish I had? It's one of those things of like, have you ever been solving a problem in math and you're like, oh my God, I would totally solve this problem in seconds if I just had this little piece of information. Typically they want you to think that because there's usually a way for you to find it. So for example, you go, oh my God, I wish there was a way for me to find the radius of this circle. Well, there is, they gave you the area, right? So 36 pi is pi r squared, so the radius is 6, right? And kind of, we'll see that written out, so you don't have to like think I just screamed that at you. But again, if pi r squared is 36 pi, that means r squared is 36, so r is 6. Perfect. So we've got this bit and this bit down pat, right? Okay, I just shared the whole answer, which is fine. So radius is 6, and the circumference of the circle is 12 pi, right? We know this because we just found the radius. So the circumference is 12 pi, and we know that this is 1/8 of the circle, right? We just told 8 congruent regions. So 6 plus 6, 2 radii, plus 12 pi over 8, which is 1.5 pi, gives us 12 plus 1.5 pi, which is C. You could have also alternatively found this angle and then found this to be 1.5 pi. Totally valid as well. You would have found that angle to be, what, 360 over 8, 45 degrees each. And so this would be right here, would be what? It would be 12 pi times 4 over pi or something. Or I think you get something like that. So you could do that math as well, and you could first find this angle and then multiply it by circumference over 45 over 360 times circumference over or arc length over circumference, and gone and done your math that way. That would have gotten you the exact same answer. But in this case, we knew that this was 1/8 of the circle to begin with because we're told. Alana, so this 1.5 came from 12 pi over 8. So 12 over 8 is equal to 1.5. And the reason we know that it's 1/8 is because we're told in the problem it's divided into 8 congruent regions. So 1/8 of the circle, 2/8 of the circle, 3/8 of the circle, 4/8, 5/8, 6/8, 7/8, right? 8/8. And so we know that this is 1/8 of the full circumference, 12 pi, right? We know the circumference because we found the radius. And so we found the circumference, and 12 over 8 is 1.5. All right, so let's start talking about polynomials, right? Everyone's favorite. We're also going to talk about exponentials and rationals. And personally, then why is it plus 12? Because we have 2 radii as well. So we want the perimeter of one of these regions. And so 2 times the radius. So 6 plus 6 is 12 plus the 1.5 pi, and that's answer choice C. Yeah, so Jarmick is putting it well, right? 2 times radius is 12. Yeah, it just so happens that this 12 does not correspond to this 12. It just so happens that 6 times 2 is equal to 12, right? This could be just the same. This could be 3, right? So you've gotten 3 plus 3 plus 1/8 of whatever number this was. Actually, there is a relationship there. That's because the circumference is related to the radius. But yeah, so that's how we got it here, right? This 12 is not this 12, right? They're 2 different 12s. Well, they're the same number. You know what I mean? Okay, so let's start talking about some algebra. We spent all this time in geometry land, and we'll get back there. Let's start talking about polynomials. So a polynomial is just an expression with multiple terms in the form where x is being raised 2 powers, right? We've all seen polynomials before. So we know a polynomial looks like ax to the n plus bx to the n minus 1, so on and so forth. That could be a cubic, right? N equals 3. That could be a quadratic, n equals 2. It could be a quartic, n equals 4. A quintic, and n equals 5. You could have a bajillionth degree polynomial. But in general, the SAT will be asking you about first, second, and third degree polynomials, right? Linear, quadratic, and cubic. So if we look at these examples, how many of these are polynomials? A and D. right? The reason why b is not is because it's not x raised to a power, it's something raised to x. This is an exponential. And the reason of this is that this top and bottom, each of those are polynomials, but this as a whole is a rational function, right? It is the quotient of two polynomials. And the reason it's not a polynomial itself is because they do not divide each other evenly, right? We'll talk more about what that means and what rationals are. But we can see that A, right, we have a fourth degree polynomial, a quartic, and A, we have a quadratic. And quadratics we'll really get into in, I think, the next slide. Yes, we will. All right, so quadratic is a polynomial of exactly degree 2. I want to push that, right? Not 2 and above, not 2 and less, 2. Below that, we have linears and just numbers. Above that, we have cubics and quartics and quintics and, but a quadratic is a polynomial of degree 2. So we have a standard form of ax squared plus bx plus c. And a, b, and c are just constants, right? They're just numbers that define what that quadratic looks like. X is a variable, it's an input. A, b, and c are constants. They don't change ever for that specific quadratic. However, not all quadratics are always written like this. They always can be written like this, but they're not always given to you like that. And we'll talk about some methods to solve them. But we have a few methods, or a few kind of forms they can take. Right? We have this, that's standard form. This, which is still standard form, but note that b in this case is 0 and a is 1. Right? So we don't have a b term. We call it what I'll be referring to as the linear term. C is not a quadratic. Why? Because it has a fourth degree power, and so it's not a quadratic. D is, right, it's in what we call vertex form. We have a square on that x and nothing else. And E is in what we call factored form, right? It's the product of two binomials. And we'll get really into kind of each of these forms and what they mean for us as we go through. And yeah, so just as some nomenclature here, because I'll be using it, I call ax squared, this right here, this is the quadratic term. I call bx, this is the linear term, and c is called the constant term, right? And that's because this defines it as a quadratic. This is a linear relationship with x, right? A constant bx. And then c is constant, right? It's just c. So just as I refer to it when I say, for example, oh, a quadratic without a linear term, that just means a quadratic without a b. If I say, oh, well, we can just divide the quadratic term by 2, that means a right here. So just some language that I'll be using throughout. And I'll be kind of noting that as I go through. So here's a simple practice question, and kind of I'll go through it quickly. So for the function g defined above, a is a constant and g of 4 is 8. So what is the value of g of negative 4? So here we have a quadratic right there with some a value that we want to figure out, right? And we know that g of 4 is 8. So when I plug 4 into this right here, so 16a plus 24 is 8. We can solve for a to be negative 1, but we're not done. It's not asking us what is a, right? If you put c, you'd be wrong. The question is asking what is g of negative 4? Well, we know that a is negative 1, and so we know that g of negative 4 is negative 4 squared plus 24, which is 8, which gives us an edge choice of a, right? That's just plugging in this value of a we found into this function and plugging in negative 4. So pretty simple. You could have also used a number of other kind of logical answers, like, oh, well, parabolas are symmetric, and this is doesn't have a linear term, and so it's symmetric about the origin. You could have done a ton of stuff like that, and not had to go through all this algebra. But in case you didn't know that, there's algebra you could always do, right? And again, there's some easier ways to do this. But this is kind of the way to do it that I would do on the SAT when I'm not thinking about the complex properties of parabolas and whatnot. All right. So that's kind of how we use quadratics in math, right? And what defines a quadratic is those a, b, and c terms. So how do we factor a quadratic, right? Well, what can we think about factoring as, right? What is it? Well, factoring is just undoing the distributive property, right? If you can think of two items of a sum or difference having the same kind of multiplicative factor, we can factor it out because actually what's been done is some implicit distribution. So for example, 3x and 6 are both divisible by 3. So we can write this as 3 times x plus 3 times 2. And then we know that actually it was a distributive property, 3 times x plus 2. right? That's with another way of saying that is 3x and 6 have a common factor of 3. So again, factoring is a puzzle about figuring out what two things multiply to get the big thing. So in the sense of a quadratic, we want to figure out not just what two numbers or what number multiplies, but actually what two binomials, right? Every quadratic can be written as a function of two binomials being multiplied by each other. And the reason is, well, we need an x term here and an x term here. And the reason for that is that we need an x squared at the end. So if we distribute this out, we FOIL, we get x squared plus fd plus dx. So we can simplify that to d plus fx plus df. And that's our standard form for the quadratic. And so that'll be useful in figuring out how we figure out what number is this factor to. So in particular, if we're given some quadratic, right, in this case, x squared plus bx plus c, we need to find then what is d and f. We know that d plus f is b and df is c. So we just want two numbers that fit those two properties. So let's look at an example, and that might make it a little more clear, right? We have the quadratic x squared minus x minus 20, and we want to factor it, right? We're told it's equal to x plus a, x plus b, and to find a and b. Well, we know from before, right, this is our form for factoring. dab is going to be negative 20, right? Don't forget that negative. And a plus b is negative 1. And so this is just some trial and error, right? We think through, okay, well, what numbers multiply to 20, negative 20, okay, 5 and 4, 3 and something, 2 and 10, 10 and 2, 20 and 1. And we get to negative 5 and 4, or vice versa, right? 4 and negative 5, right? Multiplication is commutative. So using trial and error, we find these two numbers, plug them into x plus a and x plus b, and we find our factored form. And we'll see why this is really useful later, right, in solving quadratics. But for now, just think of it as a really useful way to simplify a quadratic into linear terms that we find useful, right? Two linear binomials. So the caveat here is that this only works when a is equal to 1, right? Because if we do this x times x, that's going to get us 1x squared. So if this is like 3x squared, we have to figure out, well, then 3x squared plus, oh, now we have 3f and df, so we have 3 plus something, and right, that screws everything up. So we need another method of factoring that allows us to have an a term instead of just being 1. And that's where factor by grouping comes in. The only big difference for here really is figuring out, instead of figuring out two numbers that multiply to AC or multiply to C, we want to find two numbers that multiply to AC. And that's because this 3 here now impacts this term right here, right? And this term. It impacts these two terms. And so we need to find out how to split up this in a way that makes it factorable, and how to split up, find two numbers that multiply AC and add to B, right? So again, add to B, just like before, and multiply now to not just C, but to AC. And you can figure this out if you kind of multiplied it through. So in this case, I think an example makes this a lot clearer. So we're given this quadratic, and we're asked which of the following is equivalent, right? So it's asking us to factor. So we want to figure out two numbers that add to 10, just like before. Excuse me. Two numbers that add to 10 and multiply to 24. That's exactly what this was asking us the whole time. Second. Okay, perfect. Okay, so well, if we think again, this is some trial and error. Okay, well, we have what numbers add to 10? 5 and 5, 2 and 8, 6 and 4, right? We find 6 and 4. All of this is kind of trial and error. They'll always give you numbers that are relatively easy to use. And so we want to split that 10x and form groups. And the reason we do this is because it allows us to find greatest common factors, right? So instead of just kind of figuring out the numbers, we now have to actually undo the distributive property by breaking the pieces down and then building them back up. So here we break it down, and we kind of look at them as groups right here. We factor this in x out of here to find x times 3x plus 4, and we factor a 2 out of here to find 2 times 3x plus 4, right? What do you know here? We have a greatest common factor, 3x plus 4, that we can then factor out to get x plus 2 times 3x plus 4, and that is answer choice C. So it's a process that kind of just, you really just have to work problems, and that will get you comfortable with it. There's very little logic I can apply to it that I could apply in a few minutes that will make it like click in most people's heads after just learning it the first time, because it feels like an arbitrary algorithm. The best I can say is think of it like the same thing we're doing here, just now that this whole thing is impacted by the fact that we need a certain term here. And so we have to find new numbers that multiply to different things. So now we're talking about how to factor them. Well, how do we just solve quadratics, right? So actually, I'm going to move forward a slide here real quick. A couple slides. Wow. Is this even here? Oh, it's not here. Okay. There's another slide in another presentation that, okay. Putting that aside. What do we mean by solving a quadratic? When we talk about solving a quadratic equation, we're usually referring to how to find the roots of the quadratic, the roots being where it equals 0, right? If you graph a quadratic, that's where it crosses the x-axis, right? So if this is the x-axis, we have our quadratic, those couple points right there. My arm is not a great x-axis, but those 2 points right there would be the roots of that quadratic, and that's what we're interested in finding. So for example, we can oftentimes solve for that just via square roots, right? That's everyone's first instinct is, well, I know how to do reverse order of operations from algebra, so let's just take square roots and figure it out. This is only useful when you don't have a linear term, because the square root of like 4x is not 2 or 2x, it's 2 radical x. And so we can't do anything from there that's really helpful to us. And specifically also, the square root of 3x squared, for example, plus 4x is not square root of 3x squared plus the square root of x, or something like that, or 4x. You cannot split square roots like that. And so that's why they're really not useful for anything, unless you can isolate your x squared term. So here in this case, for example, we can add 6 to both sides, divide 3 by 3, and take the square roots. That's really easy, right? It's usually really obvious when you can, because it's your algebra brain goes, oh, I can solve for this like it's a regular algebra expression. So that's really useful. One thing to never forget, when you take the square root on both sides, add your plus or minus, right? Every quadratic, every quadratic will have 2 roots, right? One of them or both of them might be complex, which we'll talk about later, but they always have 2 roots. It's called the fundamental theorem of algebra. Not something new for the SAT, but I think it's interesting. So that's a really interesting and useful method, kind of the most straightforward one. Factoring, right? If we have this factored form of a quadratic, well, we can use what's called the zero product property to find that it's always going to be 0 if either this equals 0 or if this equals 0. So we just want to find those 2 situations. When is ax plus b equals 0? Solve. When is cx plus d equals 0? Solve. And we can solve that like algebra. So that's kind of a really useful method if it's easily factorable. So for example, we had that example from earlier. Well, we know now x minus 5 and x plus 4. When are each of those equal to 0? When either x equals 5 or x equals to negative 4. And those are our 2 solutions. Completing the square, we'll talk about that in detail on the next few slides. And the quadratic formula, right? Our holy grail of quadratic solutions. That's the formula right there. You do have to memorize this. You should have it burned into your brain walking into that exam, because it can solve every quadratic. We'll be talking about a little later kind of why you shouldn't just use it always. Typically, it's just very arithmetic heavy, very computation heavy. I don't like it. I think it's really ugly. And so use with caution, but use it when you want to use it. It's always there for you. Specifically, also note that you can only use it after you've turned it into this exact form where you know your A, B, and C. So we talked about a few methods, but it's time to talk about what I think is the most elegant and my personal favorite method, which I don't call it this, everyone calls it this. It's completing the square. So completing the square is useful when the linear term, b, is even, and we'll see why. Because we're going to end up dividing it by 2. So it's always possible to complete the square, even if this b term isn't even. It just gets real messy real quick. It's not a fun process. But it is fun when this b term is even, and you'll see why. It's because it turns our quadratic into a situation where we can solve it by square roots. It's like a machine that takes a quadratic and turns it into a very nice creature that we can interact with. So completing the square will come in handy with circles. We'll see that in some examples. But let's take a look at a quadratic example first. The quadratic of x squared minus 6x plus 8 equals 0. I actually chose this example really poorly because you can really easily factor it. But yeah, 4 and 2. There you go. Or -4 and -2. There we go. Yeah, so you could easily factor it. But let's complete the square for just to humor me, right? So our first step is going to be to isolate our x terms, right? Because we're going to be essentially turning this right here into a perfect square trinomial. And what a perfect square trinomial is a trinomial that is something like x plus 3 squared, or x plus 4 squared, or 2x plus 7 squared. So it factors, into two things, right? Or it factors into the same thing twice, right? It's a square. It's a perfect square. That's why it's called completing the square. We want to find that missing piece to literally complete the square. And the way we do this is by adding b over 2 squared to both sides. So here we added 9, right? -6 over 2 squared. That means we can factor this right here into a perfect square trinomial, right? And the way you want to do that is just by recognizing that this is the same as x minus 3 and x minus 3, right? You can factor that like normal. And from there, you can use square roots, right? You might be going, well, wait, but we're going to have a b term, whatever. Right? You can't solve this by square roots, but it's equivalent to this. And if we take the square root of both sides, we get x minus 3 is equal to plus or minus 1. So we know that x is going to be 3 plus or minus 1, which is 2 or 4. That's the elegance of completing the square. It lets you turn a quadratic that otherwise wouldn't be solvable by square roots into a quadratic that's solvable by square roots because you've literally completed the square. You've taken this thing that's not a square, morphed it, and turned it into a square. You've completed the square. This is not a completing the square practice. This is a calculator practice. But I'm going to just go through it because we are running short on time. So we have this equation right here, h equals -4.9t plus 25t. And we are told that this equation is the height of a ball after it's been launched. And its initial velocity is 25 meters per second. That's where this 25 comes from. After how many seconds will the ball hit the ground? So we want to find when is h equal to 0. We have two situations. Well, this is a calculator question. We could have just rounded up to 5 and then kind of done the math, but it's also just easier to graph, right? So I graphed this on my TI-84, and then I used some functions on the TI-84 to find that 0. And that 0 is 5.1, roughly 5 seconds. So it's really just an exercise in using your calculator. Okay, I know we just did a lot of math. We got plenty more. But it is unfortunately my time to leave y'all. And Tammy's going to be taking us home through the rest of exponentials and geometry and rationals, everything. Thank y'all for sticking around. And yeah, I'll pass it off to Tammy.
All right. Okay, guys, let's talk about exponential equations. So what are exponential equations? So they're the type of graphs whose growth rate increases over time, proportional to itself. So as the time goes on, it's not increasing by a constant factor, like for example, 2. Instead, it's increasing by a constant rate, like 2x. And yes, an exponential function takes the form of f of x is equal to a times 1 plus r raised to x, where a is that initial value, r is our growth rate. And an example of this would be the population that doubles each day, compounding interest, simple interest, etc. And visually, it looks like something, the graph that you see on the top right. Now, what is exponential decay? So it's basically the opposite of exponential growth. Instead of growing, it's decaying or going down. So as the time increases, the growth is reducing or decreasing by a constant rate. Now, this one's form is very similar to our exponential growth one. It's f of x is equal to a times 1 minus r raised to x, where r is the decay rate. Yep, and that note is just that it's the same as the exponential growth, just with a negative growth rate. So keep that in mind when you're memorizing that formula. All right, let's move to the next slide, please. Okay, so we've got a quick refresher of exponent rules. Um, yeah, what's a better way to practice this instead of just practice it? So if I say, for example, x times 3 times x times, or x raised to 3 times x raised to 5, that would be x raised to 8. And you guys can chime in the chat if you want. And then, for example, another example would be x raised to negative 2 would be 1 over x raised to 2. And x raised to 1 over 8 would be the 8th square, or the 8th root of x. And it's just like the square root of x is the same thing as x raised to 1/2. Another one, let's see, 2 times, or x raised to 2 times 3 would just be x raised to 6. I'm sure you guys know all of this, so I'm not gonna like go over it, but it's very good to keep in mind. Remember that x raised to 0, anything raised to 0 is always equal to 1. And yeah, just refresh on these. These are important. Let's move to the next slide. All right, we're going straight into practice here. The answer is right there, but let's go over the problem. So we're asked for what is the y-intercept of the function f of x is equal to 4 times 2.9 raised to x. So the y-intercept occurs when x is equal to 0, right? So that's basically all we need. That's all the information we need to solve this problem. All we do to find our y-intercept is to plug in every time x is in the equation for x is equal to 0. So when we do that, we get 4 times 2.9 raised to 0, giving us 4 times 1, which is equal to 4. So our answer is A. Okay. Next question. We have another? Yes, we do have another question. We're going straight into modeling linear and exponential growth. These are very popular questions in the SAT. So we've got this question: suppose a business sells lemonade on a hot summer day. A cup of lemonade costs $3 and the business begins with $10. They sell lemonade at a constant rate, and after 2 hours, they have sold 4 cups of lemonade. Which of the following function models the revenue R made by the lemonade stand at the function of t, the number of hours it has been? All right, so take a minute and try to solve this problem. Yeah, go.
You saw nothing. I didn't show the answer by mistake.
You're good. Okay, guys, hope you got a chance to think about that. Let's move to the answer on the next slide. All right, so we've got our answer is B. What was option B? Sorry, let me pull it up real quick. It was 10, R of t is equal to 10 plus 6t. All right, thank you, Dylan. Yeah. Okay, so let's talk about it, right? So the cup of lemonade costs $3 and the business begins with 10. And notice that they're telling us, this is the key for this question, they're telling us that the lemonade is sold at a constant rate. So every hour, they're selling a constant number of cups of lemonade, right? So they're saying in 2 hours, they sold 4 cups of lemonade. And if we know that it's constant, since they mentioned it, that means for every hour they're selling 2 cups of lemonade, right? So that's our rate, 2t. Or there's more for that, but every cup, so we know that they sell 2 cups per hour, and every cup costs $3. So therefore, every hour they make $6 because they're selling 2 cups of the $3 lemonade. So our rate is 6t, right? Every hour they're making $6. And don't forget the fact that the business begins with a profit of $10. I don't know how they got that, but it begins with $10. So therefore, our revenue equation or revenue function would be 10 plus 6t. Hope that made sense to everybody. Definitely ask if you have questions in the chat. We can move to the next slide. Okay, let's talk about rational equations. So what is a rational function or a rational number, right? A rational number is basically a number that can be represented in the form a over b, where a over b are integers and b isn't equal to 0. And that's basically the same, pretty much the same thing of what a rational function is. So they're of the form f of x is equal to g of x over h of x, where g of x and h of x are other functions. So they can be the same. And for example, the simplest rational is f of x is equal to 1 over x. So you might be asked, or you will be asked, to solve rational equations and manipulate the functions to find certain results. So we've got an example practice problem for you here, and this is pretty much what the SAT will ask you as well. Sometimes they hide it in the problem, but yeah, take a minute to solve, take like 30 seconds to solve this equation here, and basically just try to simplify it as much as you can. All right, 30 seconds. Sure. Sorry, Yanni. Thanks for asking. Okay, let's talk about it. Let's get those transitions in. Okay, so we've got our function here. All we have to do is take one part of the equation to the other side. So that's what we did here. We distribute that 8 to our function 6x plus 3. And once you do that, you just isolate for x to get negative 5 over 23. Does that make sense? Yeah, why? It's just an arithmetic error. Okay. Okay, yeah. But yeah, this is pretty much the problems that you will be asked a good majority, especially in Math 3. So yeah, definitely practice those. Yeah. Okay, let's move to the next problem. Or yeah, next. Okay, we've got another rational expression here, so we can practice that again. Let's take a minute to solve this one. Okay. Okay. Let's talk about this one. Move to the next slide. So here, all we have to do is, since both equations on the left and the right has numerators and denominators, we want to cross multiply to get 5x plus 100 is equal to 15x. We can solve for x, and we get x is equal to 10. But notice how they were asking us for 5 or x over 5 rather than just 5. So all we have to do is just do 10 over 5 to give us 2. So our answer is C. Pretty simple, but you can see how they can catch you if you're not paying attention. Okay, next slide. Oh, we've got more practice. Okay, what is the solution set for this equation above? Okay, I swear this one's a little different from the other ones. Let's look for an explanation on the next slide. Okay, so how we're going to be approaching this one is probably, all of you guys know, just like square both sides to get rid of that square root. So once we do that, we get left with this second line that you see here on the right. And then you put that in put the quadratic in standard form, which means put everything on one side and the other side should equal 0. Once we do that, we can factor and we get two solutions. We get -1 and 5. But is that the answer? Is that the answer? It's not. Plugging in works, yeah. But this is not the answer, and why is that? It's because when we are given a problem like this, we want to find the x value for which it equals the equation, right? So factoring isn't going to help because we're equating that to 0. Oh, sorry. And because we're equating that to 0. So if you plug in these two values that you get here, you won't get that. And if you compare the left-hand side and the right-hand side of the equation, when x is equal to -1, you won't get the same values. However, if you do it for x equals 5, then you will get the same values. You will get that the left-hand side is equal to the right-hand side, making the equation legit, right? So you always want to check that. If you want to check for, and the word for that is extraneous solutions. You want to check for extraneous solutions. Yeah, plugging in definitely works too. This is a simple problem, but the SAT does test you on efficiency. So you do want to be approaching these problems and like finishing them as fast as you can. But if you have extra time, 100%, like that is a surefire way to go. Yeah. Okay, let's move to the next slide. Okay, and yeah, this is just a graphical visual of what that looks like. Notice how the graphs only meet at x equals 5, even though x equals -1 was also a solution for the factored form of the equation. Okay, next slide. Okay, we've got some more practice. Which of the following could be the equation for the graph above? 1 minute. Okay, this one is also pretty easy to get caught up in it, but okay, let's move to the solution. The answer you should have got is option B. Now, the reason for this is, as you all probably know, like to find the equation of the graph, you just have to find what the roots of the equation, right? So what are the roots of this graph right here? So we know that, so the roots are anytime the line touches the x-axis, right? So we've got one obvious root here when x is equal to -3. We've got another obvious root when x is equal to 2, and we've got one when x is equal to 0. However, notice that the line isn't crossing the x-axis, okay? So what you want to think about is the reason why it's x squared, which people who got the wrong option, who selected the wrong option, probably didn't understand that the reason why it's x squared is because our graph or our line is hitting x equals 0 kind of twice. Since it's not crossing the x-axis, it's going up. It's kind of like a curve, right? So it's going up and it's hitting x equals 0 once, and then it's going down and it's hitting x equals 0 again. So that's the reason why it's x equal x squared, because it would be x minus 0 squared if you like want to write it out. But since x can't equal, or since x minus 0 doesn't mean anything, it's just x squared. Hopefully that made sense to everybody. Okay. So let's move on to the next equation, or yeah, next topic. We're talking about geometry. Yes. Okay, I love geometry. Let's do this. Okay, we've got volume word problems is what you're going to be dealing a lot with in the sector of geometry. So these formulas are given to you on the SAT, so you don't have to memorize them, but it will save time for you to like kind of familiarize yourself with them, know that they're there. So yeah, it's just in your best interest to like familiarize yourself. If you memorize, that's perfect too. That's really great. So many of these problems will require volume without being explicit about it. They won't just be like find the volume, but instead they'll kind of hide it in the problem. So we've got a practice problem right here. We're told that Bob has tanks of gas in the shape of a right circular cylinder with an internal diameter of 3 feet. He pours gas from a gallon jug into each until it is full. So if the height of the jug is 6 feet, what is the largest number of full jugs Bob can fill with 1,000 gallons of gas? And this is something the SAT often does. They won't expect you to remember that, oh, 1 gallon is this many cubic feet. They'll just tell you. So we've got a note here that says 1 gallon is equal to that many cubic feet. So the way on how to solve this is we need to know our volume equation of the right circular cylinder, which I believe is given to you on the reference sheet. So the volume is pi r square h, where h is height and r is radius. So we're already told that we just plug in all of those values that we've gotten from the equation. Diameter is the half of radius, or 2 times radius. So to find radius, we're just taking that diameter and dividing it by 2 to get 42.411 cubic feet per jug. So once we have that, so that is how much volume the jug can hold, right? Now we have 1,000 gallons, and we want to see how many jugs, how many 42-ish, how many jugs that can hold about 42 cubic feet does it take to get rid of the 1,000 gallons, right? So all we do, that's just a proportion, and all we have to do is take 160, 160.544, which we got by multiplying the 1 gallon proportion times 1,000 and dividing that by 42.411 cubic feet to get about 3.78 jugs. So Bob can fill a max of 3 full jugs with 1,000 gallons of gas. Does that make sense to everybody? Okay. All right, let's move on. Okay, this is a practice problem for you, so take a minute and try to solve it. Go. Okay, so this is a really neat problem because they basically gave us the volume equation and they've also given us the volume. So we've got our equation, we can equate it to the volume given in the problem, which is 473, and then we can just solve for k, right? So this is just some algebra heavy work. So yeah, like I said, just multiply 48 by both sides, divide by 7 pi, and take the cube root to find k. And that is 10.11, which is option D. Right. Let's move to the next slide. Okay, let's talk about right triangles. So this one is another really important topic. So we've got two fundamental right triangle theorems or patterns to remember. We've got the Pythagorean theorem, which is a squared plus b squared is equal to c squared. This is like this is the main function when you're dealing with right triangles. We've got our special right triangles, which is the 44, 40, or 45, 45, 90, and the 30, 60, 90. And if you look on the bottom, you can see the sides corresponding with those angles. That is, I believe that's also given to you on your reference sheet. That is really good to keep in mind because it's just like there are problems that are going to ask you about that. So you want to remember that it is on your reference sheet, even though you can't memorize it. Besides that, we've got the area formula, which is 1/2 BH. And then two acute angles and a right angle add up to 90 to remember that. And yeah, outside of these rules, the majority of the triangle problems will relate to congruence and similarity. Okay, let's talk about congruence and similarity in the next slide. Okay, so congruent triangles have the same length, sides, and angles. But similar triangles have the same angles, but they have proportional side lengths. So let's look down at the two triangles we have on the left side of our screen. So in this case, triangle ABC is congruent to triangle XYZ. So this means that all these sides divided will give us a value k, where k is the scale factor. So this means another way to think about it is if you take sides BC and you multiply it by k, you're going to get the side x, or you're going to get the side YZ. Similarly, if you do side AC and you multiply it by k, you'll get side XZ. So that's basically that scale factor, what we're multiplying each side to make an equivalent or a similar triangle, not an equivalent triangle. Okay, so that's what similarity and congruence are. Let's move to the next slide. Okay, we've got a triangle angle problem. The answer is already here, so I'm going to go over it. So yeah, we've got this one. Let's start with the line, the 106 angle. We know that if there's a line, the whole angle would be 180. And we're already given that one part of that 180 is 106. So to get A, all we have to do is we take 180 and we subtract 106 to get A is equal to 74. Once we have that, we see our we can see a little triangle between A, angle 23, and angle B. And we know that all the angles of a triangle always add up to 180. And we know that A is 74, we already have 23, so we just add them up together, equate that to 180 to solve for B, which is 83. Once we have B, we can once again use that a line equals 180 to get 180 minus 83 to solve for x, which makes x 97. So yes, we were asked for the value of x, so the value of x is 97. All right, next slide. Okay, special right triangles practice. So what is the length of AD? So it is clear that these triangles are congruent because they're the same angles and like same side length. So therefore, AB is equal to 12 because they're congruent and they have the same side lengths and the same angles. And then by special right triangles, this is where that's important. It gives us the side lengths. All you have to do to find the side opposite of 30 degrees is 2x, and equate that to 12, which makes x equals to 6, and AD is equal to 6. All right, next slide. Okay, let's talk about complex numbers. This might be, yeah, I think this is one of the last topics. So, Iani, no, all the sides do not equal, or, well, we're looking at two different triangles here. We're looking at ABD and DBC. But yes, all the sides of this triangle ABC does equal 12. Yeah. All right. Yeah. Okay, next slide. Okay, complex numbers. So what are complex numbers, right? Complex numbers are basically when taking the square root of -1. It's not a real number, but it's an imaginary number. So all these mathematicians came and thought, like, it's not possible. We all know that it's not possible to take the square root of -1. But the mathematicians came together and be like, what if it was possible, though? And they made this whole new coordinate system based on this idea that this imaginary number I equals the root of -1. So based on that, all imaginary numbers are multiples of I. So a complex number has the form of A plus BI, where A is a real number and BI is an imaginary number. And you are likely to have at least one question about this, so definitely review this, pay attention. But yeah, remember that a complex number has the form of A plus BI. Okay, let's move to the next slide. Okay, so adding and subtracting complex numbers. So complex numbers are treated like binomials. When adding and subtracting them, we combine the like terms, and so the real with real and imaginary with imaginary. So all the i's come together and all the a's come together, right? So for example, what is the sum of 7 plus 3i and 8 plus 6i? All you have to do is once again join the like terms. So 8 and 7 and 3i and 6i, you get 15 and 9i. So 15 plus 9i is your answer. Let's try another example. Subtracting. So if a is equal to 9 minus 4i and b is equal to -4 minus 7i, what is a minus b? All we're doing is we want to subtract that. So let's see the answer. Don't forget that when you gotta distribute that negative sign, to give us 9 minus 4i plus 4 plus 7i, giving us 13 plus 3i. Yep. So yeah, pretty simple, right? Just make sure to real with real and imaginary with imaginary. Okay, next slide. Multiplying complex numbers, we want to keep in mind that since I is equal to the root of -1, I squared is equal to -1. And then to multiply, move to the next transitions, we want to FOIL it out. So we want to, take the inside and distribute to the other one and so forth. You guys know how to FOIL. We want to replace the I squares with -1 to make the I squared term into a real number. So once we replace the I squared with -1, it's no longer imaginary. It crosses the realm to the real numbers, right? And then we want to do the same thing like we always do. We want to combine like terms and write the result in the form of a plus bi. So for example, what is the product of 3 plus 2i and 5 plus 7i? You guys want to take a minute and solve this? You can take about like 30 seconds. Okay, 30 seconds. Okay, let's see what the answer is. Okay, so we have that. We're FOILing it out to get 15 plus 21i plus 10i plus 14i squared. Notice the 14i squared, we know that I squared is equal to -1, so we can immediately plug that in there. Yep, and just like Iani mentioned, it is 1 plus 31i. Great job. Okay. Now we're going to talk dividing complex numbers. This one's a little different, and it has to do with multiplying with the conjugate of our complex numbers. So we want to follow these steps. Yep, that's a lot. So basically all you want to do is you're given, when you're dividing, you're given a denominator and a numerator, right? Or a numerator and a denominator. So what you want to do is you want to multiply both the numerator and the denominator by the conjugate of the denominator. So what that means is, if you look between all these words, the conjugate of, for example, 7 plus 8i is 7 minus 8i, right? So all we're doing is we're multiplying that by the numerator and the denominator. And notice how that's not changing anything, right? Because 7 minus 8i over 7 minus 8i is just 1. And multiplying anything by 1 is just the same thing, right? It's not going to change. So our goal here is basically to not have a complex or our imaginary number in the denominator, because that makes it look complicated and messy. We want to put it all up to the numerator. Okay, so let's try a practice problem. Since I didn't go over all the steps, I'll kind of go over it now. So our example is a is equal to 4 minus 3i and b is equal to 2 plus 1i. I forgot to add the I. What is A divided by B? Okay, let's go over the answer. Okay, so we've got this. We've got our denominator is 2 plus I, right? Oh, it's not 1. Yeah, it's 2 plus I. And what we want to do is we want to multiply our numerator and our denominator by the conjugate of 2 plus I, which is 2 minus I. So we're going to multiply. We're going to FOIL it out to get all of that. And then once we get 8 minus 10 plus 10i plus 3 times -1 over the denominator, we just simplify it out to get 5 minus 10i over 5. Simplify that a little bit more further to get 1 minus 2i. Pretty simple, right? The only thing you need to be remembering is to multiply by the conjugate. All right, next slide. Okay, we've got some practice here. So let's solve this problem. Take a minute. Okay, so we're given a division problem. We learned how to do this. So how to solve it is, let's move to the next slide, is to multiply by our conjugate. And our conjugate in this case is 1 plus I. So we're multiplying that. We're foiling our equation out. We're grouping it together, the real with real and imaginary with imaginary. We divide it, we get 2i over 2, and we divide out 2 to get our answer is I. So it would be option A. Okay, let's move to the next problem. Okay, so now we are on to practice, which is basically everything that we've learned in this stream. We're going to attempt to do a couple of problems. So let's move to our first problem. Okay, we've got this quadratic equation, or we've got this equation, and which of the following is equivalent to the expression above? All right, this might take more than a minute, and that's okay. So, all right, take a minute. Okay. Does anybody need more time? Okay. All right. Let's go over it. Okay, so the understanding here is that you know so this is like a little messy because it's not our greatest factor isn't x or a raised to 2, but it's a raised to 4. But what we want to understand is that a plus b squared is equal to a squared plus 2ab plus b squared. And that's the understanding that you want to have. So all you have to do with this equation is you want to kind of simplify it in terms, you want to make it in terms of that equation that I just said, right? A squared plus 2ab plus b squared. So how to do that is basically we're going to look at this equation that we have right here, and we're going to say 9 of a times a to the raised to 4 is equal to 3 a raised to 2. And we can do that in the same way. And then 12a squared b squared is equal to 2 times 6 of a squared times b squared. So that makes sense. And then 4b raised to 4 is equal to 2b raised to 2, the whole squared. And that's kind of written out for you right here as well. And once we have that, we can notice that our a value is 3a squared and our b value is 2b squared. And we know, and that can just be simplified down to 3a squared plus 2b squared, the whole squared, because of our form of a plus b squared is equal to a squared plus 2ab plus b squared. I know that's a lot to take in right now, but you can watch the replay, listen to me say it a little bit more slower, but that's basically how I got that. So our answer is option A. All right, let's move to the next problem. This is another complex number division. So yeah, let's take a minute and try to solve that. All right, so this one is just like our the problems that we've practiced before. All we're doing is we're taking the conjugate and multiplying that by our numerator and our denominator. So let's do that. Let's get the answer in there. Yep. So we're multiplying it by our conjugate. We're FOILing it out. We remember that I squared is equal to -1. So we plug that in for our equation. We get 7 over 4, or 7 over 34 minus 28i over 34. And yeah, that's our answer. So our answer is option C. Okay. Okay, our next problem is a dairy farmer uses a storage silo that is in the shape of the right circular cylinder above. If the volume of the silo is 74 pi cubic yards, what is the diameter of the base of the cylinder in yards? All right, take a minute and try to solve that. All right, guys, let's take another minute to solve this. Okay. Sorry about that. Okay, cool. So we've got all this information here. We've got our volume of the cylinder. Okay, let's view our solution. Yep, thanks. So our volume of the cylinder is pi r squared h. We've got our volume is 72 pi. So all we have to do is solve for r, because that's the only thing we don't know. We solve for r, we get r is equal to 3. And now here's the key, right? The diameter is 2 times the radius. So all we have to do from here to find the diameter is go 2 times r. And that's 2 times 3, and that is 6. Oh, Kaden. Oh, you said you didn't see it. Okay, because it divides out because of the pi on the formula equation. Okay? All right, cool. Let's go to our next question. This one's a little hairy, so yeah, take a minute. All right, guys, let's take like another minute because I think this takes a little bit more time. All right, guys, let's talk about this one. So we're asked to find an equation for which the coordinates of the vertex of the parabola A can be identified. So this is just another way of them asking you to put it in vertex form, put this quadratic formula to be, or the quadratic equation to be put in vertex form. And how we do that is we do that through completing the square. So let's look at the answer. Okay, you guys were right about it being D. So all we want to do here is, remember that vertex form just means H and K is the vertex. But yeah, so to put in vertex form, all you do is you want to take the B value, which is -2, and we want to divide that by 2 and square it to get 1. And then we isolate 15 on one side, add 1 to both sides of the equation. That's how we got 16, by the way. We factor out our right-hand side, which is x squared minus 2x plus 1. We bring 16 back from the other side of the equation, and we get 1 minus x minus 1 squared minus 16 as our answer. So that's choice D. Great job, guys. I see y'all in the chat. Okay. I think we're about done with our questions after this one. Can everyone hear me, by the way?
I can hear you okay.
Sorry, one second.
Thanks, everyone. Make sure to fill out the survey. It's in the green button at the bottom of your screen. And you can rewatch the recording if you were confused on anything. Have a good night.